Welcome everyone to this video on the background of dual energy CT. I'm going to give you a bit of a warning from the top. I may lose some of you briefly in this video. We're going to get into the nitty-gritty of some CT physics and how it applies to dual energy. Now, I don't need you to have a full understanding of this. This is just to give you a background so that we know how and why we use it clinically. So let's get started. Okay, let's get into it. So what is dual energy CT? Well, dual energy, or sometimes called spectral CT, is basically CT imaging using two different X-ray energy levels at the same time. When doing dual energy, we normally use something like 80 kV and 140 kV, so one low energy and one high energy. So why is this? Well, different materials absorb X-rays differently at different energy levels. If we sample each voxel at both of these energies, we can work out what that material is actually made of, not just what it looks like. So in simple terms, a normal CT scan gives us what it looks like. Dual energy gives us what specific material is it made of. So this is why dual energy CT can separate calcium from uric acid, iodine from blood, or metal from soft tissue. It's currently used a lot in gout imaging, CTPAs, and KUBs for urinary stones, and can be used for bone removal for vascular work, or differentiating between some of those materials we specified. So iodine versus blood in head imaging is something we routinely use this for. Okay, let's next get into how do the CT scanners actually capture dual energy data. We're going to start off with how ours in Townsville works. So ours is a dual source CT. What this means is we've got two tubes and two detectors spinning around the patient simultaneously, capturing two full true data sets. We can manipulate what kV each tube is set at, so we know exactly what spectra it's running at. And as well as this, we can put in a filter on our high energy kV, which hardens the beam and makes it even higher, which gives us gold standard dual energy with gold standard spectral separation. Another way we can do it though is single source with rapid kV switching. What happens here is one tube spins around the patient and only does one scan, but while it's doing that, it switches between low and high kV. So it can be doing this up to several hundred times per second. What happens here though is you need to slow your scan down to capture this data. Roughly 2/3 of your data will be at the higher kV, 1/3 at the lower, which means your system has to interpolate and extrapolate that data. So because of this, the data isn't perfectly aligned. Next, we've got detector-based dual layer spectral CT. What happens here is a polychromatic beam, generally at 120 kV, hits a detector. The top layer picks up the low energy photons that have reached the detector, and a bottom layer picks up the high energy. So it's a good idea. It works well, but there's limited spectral separation because both layers are seeing the same beam. You get a full scan, there's no limitation in speed though, and you do get a true data set for both spectra. Another way that can be done in some systems is a split beam technique. So here there is a filter put across the beam. It generally has two materials like gold and tin. So tin hardens the beam and gold softens the beam. So the detector is essentially split in half to match that tube, and it picks up half low energy, half high energy. So this works, but you're still running on a polychromatic beam that's split by a filter, so your spectral separation depends on how well the scanner is set up. So bottom line is dual source provides the cleanest and most accurate material separation because the two energy beams are truly separate and all data is captured simultaneous. We have no real impact in scan time, but you will notice that in the real world they are a little bit slower than our single source scans are. All right, so now it's time for the heavy physics. I promise I'll try to keep it simple and relevant, but I tend to get carried away when it comes to CT physics. So let's see how we go. Photoelectric effect. Term I'm sure is not new. Who's sitting there trying to remember it? We filed it after that physics exam at university and thought we'd never have to use it again. but we actually use it every day. It's essentially the underpinnings behind how radiography works. So it's one of the main ways X-rays are absorbed in the body, and it plays a major role in determining the attenuation coefficient. So what that means is it's responsible for much of why an X-ray beam is absorbed by a material. So when a low energy X-ray photon interacts with an atom via the photoelectric effect, the photon is completely absorbed by that atom. An inner shell electron is then ejected, and characteristic radiation or scatter is produced. So this energy then gets scattered off to the side or the back, and the detector never captures that energy. So it's seen as a loss of energy or attenuation. So the likelihood of this occurring follows the formula Z cubed over E cubed, where Z is the atomic number and E is the photon energy. Essentially, if we have a high atomic number, we're going to have a high attenuation. And if we have a low photon energy, we're going to have a high attenuation. Now, because both Z and E are cubed, even small differences in either produce very large changes in our attenuation. And how we capture this on our CT is differences in our Hounsfield units for each voxel that we're looking at. And we compare that to our two different energy levels. So if we're scanning at 80 and 100, materials respond very differently. So the further apart these energy levels, the greater the difference in Hounsfields. So if we think we've got a small difference at 80 and 100, if we can change that between 80 and 150, we're going to see really large differences in that attenuation coefficient. So a practical example of this is when we're looking at kidney stones. So our two main types of kidney stones are calcium and uric acid. So calcium has an atomic number of 20, and it's going to absorb our low energy photons relatively strongly. Whereas our uric acid has a coefficient of 6 or 7. It's going to absorb them pretty weakly. Now, even though these Z values don't seem super different, once they are cubed and we see big differences in our energy levels, it translates into large Hounsfield unit differences between the two. Now, for those of you who maybe did their physics exam a little bit more recently, you probably remember also Compton scatter. Why don't we use this? Well, it's actually largely independent of atomic number. And so because of this, Compton scatter produces very similar attenuation at both low and high energy, so it actually makes it poor for material differentiation. So what are our take-homes? What do we need to know? So our photoelectric effect is strongly dependent on atomic number and energy. Because the formula is cubed, small differences in either create a big Hounsfield unit change for that voxel. And this is the physical foundation of dual energy CT. So the photoelectric effect is what gives dual energy CT its separation power, and how by knowing what energy level we've scanned at, we can calculate roughly the Z or atomic number for that voxel. We can actually work out what material that voxel is made out of. All right, now let's look at our energy levels from our beam. We get what's called a polychromatic beam. So when we set our kVp on our scanner, it's not the actual energy of the photons hitting the patient. So when we select a tube voltage of say 100 kVp, that number simply represents the maximum possible photon energy the tube can produce. So we're essentially saying that that's the difference between the cathode and the anode. So there's going to be 100 kV difference, okay? Now, the beam that hits the patient is actually going to be a whole spectrum of energies, not a single value. We roughly say it averages out to be about 2/3 of the set kVp. So if we set a 100 kVp beam, our energy levels of our photons that reach the patient, the average of those will be 65 to 70 keV. Now, if we look at our beam here, we can see that we get large differences in our keV. So all our beams are fairly spread, right down to about 30 keV. Now, if we have a look at this, it actually shows tin filtered versus some non-tin filtered. So if we look at this 100 tin keV here, this one here is actually 120 keV. So by using that tin filter to take out those low energy photons, our lowest energy is about 50. And we sort of peak right up here, really close to what we've set it to. So we're getting roughly, we'd probably say roughly 85 keV would be your average there out of your 100 kV tin filtered beam. Whereas when we've got 120, we actually see this big beam right back here around the 50 to 70 zone. So that's why that tin filter is really useful for our separation, to make sure we've got a really hardened beam. As we can see here with our 150, that beam's pushed right back up into those really high energy levels. So that's what gives us a really good spectral separation on the Siemens scanner that we use. So it cuts out those low energy beams that aren't contributing, and it means we can get a really big difference between if we use 80 or 70 kV compared to tin 150. So another interesting thing is our K edge. So every element has a specific point where it suddenly absorbs much more energy. So it's kind of the sweet spot for attenuation. So iodine's K edge is around 33 keV. So this is closer to our low energy in our dual energy scans. And this is why when we're trying to perform contrast examinations of a single energy, we try to use the lowest kV possible to get a diagnostic scan. So the iodine is going to absorb more. It's going to look much brighter at the lowest energy we can use. Here we can also see some objects like fat have a similar Hounsfield units at both energy levels. So because they're a low atomic number, that beam's going to pass through them, and we're not going to see large differences in our Hounsfield between our low and our high energy data set. Alright, you can all breathe. The physics is done. Now you don't need to know the ins and outs of all of that. Essentially, all you need to know is that dual energy works by measuring how each voxel attenuates two different X-ray energies. And because the attenuation changes with atomic number and energy, different materials show different Hounsfield units at low kV and at high kV. The scanner does all of this magic math for us using a material decomposition algorithm, and it can pretty accurately tell us what each voxel is made up of, whether that be iodine, blood, water, metal, low fat, no fat, full cream, high calcium, high protein, soy, light, skim, omega-3, high calcium with vitamin D, folate or extra dollop. But they still can't give us milk that tastes like real milk. Alright, let's get into the fun part now, some clinical applications for how we can use that dual energy. At Townsville, we commonly use it for post-clot retrieval heads. So if we see a hyperdensity on a CT scan, it can actually tell us if that's contrast or blood. In some cases, it's actually a mix of both. As we've sort of touched on earlier, we can use it for KUBs to actually tell us the exact material that that stone is made out of. We can do virtual non-contrast imaging, in which the scanner goes through and works out what's iodine, and then removes that completely from our picture. And we can do monoenergetic imaging. So it takes the data that it knows, and if it says, all right, at this KEV and at this KEV, the picture looked like this, we can actually window that right back to 30 keV. So roughly a 60 or 70 kVp scan, and we can really boost our iodine. So for things like CTPAs, when we didn't get enough contrast on our scan to be a diagnostic study, we can give our doctors a map that they can fairly confidently prove whether something's a clot or not using that. Commonly used in gout imaging, so we can show the material of crystals, our gout crystals in our joints. We can also use it for bone bruising or marrow edema, which is what we've got this pretty picture here on. So we can actually see there's some bone bruising occurring here, which probably likely correlates with this cortical break in the bone here. And we can also do lumbar disc herniation. So we can compute all sorts of different maps. The scanner puts it into pretty colors for us, which we like. We get sick of seeing all this black and white. And it's got a lot of clinical significance. So being able to tell not just what something looks like, but what material it's actually made up of can be very, very useful in a lot of cases. So since I've just spent the last 15 minutes telling you how cool dual energy is and how useful it is, you might be thinking, well, why don't we use it for all CT imaging? If we can work out not just what something looks like, but what material it's made out of, wouldn't that be incredibly helpful? It does have some limitations. and it does have some negatives to it. So the first negative is higher doses. So dual energy was often said to be or claimed to be dose neutral to 120 kV. Now in our modern scanners, we're often not doing chest or abdomen imaging at 120. We're performing at 80, 90, maybe up to 100 kV. Specifically in cases like our KUBs, where we've got them optimized to be ultra low dose, if we scan the whole KUB region for every single patient with dual energy, whether they had a stone or not, our radiation dose to our public would significantly increase. The other is the scanner's performing 2 scans at half dose. So in bariatric patients, our low kV images often become too noisy to even be useful, and material separation becomes less accurate. Inversely, in small patients, our 150 kV would be way too high, would just penetrate the patient, and it also would mean that our maps for material decomposition aren't really useful at all. Now, another thing is creates a lot more data, can be a lot harder to reconstruct. A lot of it needs a lot of manual post-processing. There's a lot more maps for our radiologists to look through. And essentially, if the clinical question is answered perfectly fine with a single energy CT, then dual energy adds no real benefit. The negatives outweigh the positives, and this is why it has only a few cases where it's really useful. Okay, we've reached the end. Hopefully you all have a little bit more of an idea now of how dual energy works, why we use it in some cases, but not for everything. If you have any questions or would like to know some more information, please feel free to send me an email. And thank you for watching this video on the background of dual energy.